Welcome back to the show that tells you you are a quantum computer with free will, overcoming environmental decoherence through quantum error correction. My name is Justin Riddle, and this is episode 25 of the Quantum Consciousness series. In today's episode, we'll be discussing quantum error correction, the next frontier in information technology that is essential for quantum computers to become practically feasible and to finally surpass the utility of digital computers. By the end of today's episode, we'll ask the question, is biology utilizing quantum error correction to sustain human consciousness? This episode is available on YouTube, and an audio-only version is available on Spotify and Apple Podcasts. If you like what you hear today, then please like this video, subscribe to this channel, leave a comment below, or for the audio listener, write a review.
Join me deep inside the mystery of numbers. Come and have a metaphysical view. See how concepts become objects and then become qualia. Join us for an episode of Quantum Consciousness.
All right, welcome back. So a little of an intro to what you're watching. So I began this series after teaching a course at UC Berkeley on quantum consciousness. And so this series is really an extension and a sort of growth of that material, and basically an attempt to reach a wider audience and to sort of discuss these topics with you out there. So a little bit about me. I'm a cognitive neuroscientist, and I basically am using brain stimulation to better understand the role of neural oscillations in higher order human cognition and working towards developing novel treatments for psychiatric illness. Okay, so the topic for today is quantum error correction. So a bit of an outline here. I'm going to set up why do we need quantum error correction? The reason being that this is essential for quantum computers to become practically feasible. So what is holding them up? How is quantum error correction the solution? And then I'll talk about how this could be utilized in biology. And then finally, what this might mean for human consciousness. And stick around till the end because I'm going to basically throw out a, to my knowledge, novel theory on the emergence of human consciousness. Alrighty, so what is the basic pitch of quantum computers? The idea is that this is the next step in information technology. And I want to take a moment to just really emphasize how groundbreaking and how amazing this technology could and will be. So to sort of set the stage, there's something called Moore's Law, and this is essentially tracking how many bits can we put into a microchip. So what Moore observed is that roughly every 2 years, we're able to fit twice as many transistors or bits of information into a chip. And this has been going since the 70s, and I think since even longer than that. And this is kind of amazing because people every year are saying, this is the end of Moore's Law, there's not going to be any possibility of cramming more and more bits of information into microchips. We're basically hitting a limit. And to some degree, this is entirely true. We are now at the point where the distance between two different bits is on the order of nanometers. So we're down at this very, very small scale. And it's projected that around the year 2024, we will have individual bits of information that are only 2 nanometers away from each other. And so up until now, Moore's Law has been fulfilled. We've been doubling the amount of information that we can cram into these really small spaces pretty consistently. However, we're about to hit what's called the digital brick wall. And this is essentially a point where the very concept of physicality breaks down at a fundamental level. So if you've been watching the series, we're talking about quantum mechanics, where the very idea of physicality is your ability to measure and reduce a system down into a physical state. It's either here or it's there, and it's in this moment, we observe it here or there. And so what is going on is that we're hitting a point where our measurements are at such a small scale that we need to sustain sort of the physicality of the system into the future. And so when you look around you, you see a physical world, you leave a penny on your desk, it's going to stay in the heads up position or the tails up position into the future. However, at the quantum scale, at this very microscopic scale, things are constantly in fluctuation. And so it's really difficult to sustain these physical states into the future, right? We want to take a 1 and we want it to stay a 1. And we have a 0 and we want that 0 to stay a 0. And so we can create these systems where typically there's these clouds of electrons where the cloud of all of these different electrons are basically coding for a single 1 or a single 0. And wherever this cloud of electrons is, this is determining, here's a 1 versus here's a 0. However, at these very small scales, quantum mechanics takes over and these electrons go into superpositions of being multiple states simultaneously. And that sense of physical reality starts to break down fundamentally. And so we're not able to sustain zeros and ones in this sort of deterministic, stable, physical sense. So we're hitting this brick wall with digital computation, but quantum computation is on the horizon and it's coming into play right now. And so what I really want to emphasize is that quantum computers are not necessarily in line with Moore's law, which in a strict sense is basically saying how many transistors can we fit into a small bit of a microchip. However, if we sort of take an abstraction of Moore's law, which is that we really care about computational power, right? How much information can we process? Then quantum computers are sort of emerging in this moment, in this day and age, and they might pick up the computational burden, if you will. And we're at the precipice of seeing quantum computers take over in the information technology scene as being the dominant computational force. So there was sort of a landmark moment back in 2019 where Google claimed that they had reached quantum supremacy. And this essentially is a quantum computer that was able to run a computation that would take trillions upon trillions of years on a digital computer. And so, the universe would be destroyed by that time, presumably. And so the quantum computer essentially computed the solution to a problem that could not be computed on a digital computer in a practical, feasible amount of time. And so part of the computational power of quantum computers comes from their ability to potentially solve exponentially large problems. And while there's only a limited set of algorithms or certain problems that are solvable with this exponential speed up, it's really important to understand the magnitude of just how great this is. So I recently watched this really interesting video on YouTube, which is called The Incomprehensible Scale of 52 Factorial. And I highly recommend this video. I'm gonna summarize some of the points here. But the idea is that we are very bad at thinking about exponentially large spaces. So why 52 factorial? 52 factorial is if you take a deck of cards, 52 cards, and you think about all possible combinations of that deck of cards, right? So if you stack it one over another, how many different combinations of cards are there? Well, it's 52 times 51 times 50 times 49, ... down until, times 2 times 1. And this is a very large number. It's 8 times 10 to the 67th power. So it's 8 with 67 zeros coming after it. And this is a shockingly big number. And so the maker of that video says, you can be confident that if you shuffle a deck of cards, that exact pattern of cards has never occurred in the history of the world. And that is really mind-blowing. But to emphasize how wild this is, how many grains of sand are there in all the beaches on the planet Earth. There's roughly 10 to the 16 power different grains of sand. So if you were to take a grain of sand, label it, scatter it across the beaches of the Earth, and then go pick up a random grain of sand anywhere on the planet, and then say, was this my grain of sand? The chances that you on your first try picked the correct grain of sand is astronomically more likely than getting a deck of cards to be shuffled twice in the same pattern. The author of that video even talks about take a random proton or neutron and then shuffle it among all protons and neutrons in the Earth on the surface and including the entire core of the Earth. That is still only 10 to the roughly 40th power or something like that. And so the deck of cards is still so many orders of magnitude greater than even atoms in the planet, right? And so this also applies to quantum computers, because as you have a quantum computational system that's growing in complexity, the idea is that you can search these very large exponentially increasing spaces in a polynomial time. And once again, there's only a limited number of algorithms that we've discovered, and the number of algorithms that we're learning and creating for quantum computers is still an open space of growth and development. However, the quantum computer is able to tackle these extremely large spaces. And so to sort of wrap your head around this, a quantum computer that has 200 quantum bits is going to basically tackle the size of space of the number of patterns that you could have a deck of cards. So I know there's a lot of moving parts here to think about, but essentially the real appeal of quantum computation is that it tackles these exponentially large spaces. And so you can have the biggest digital supercomputer known to man, and even though it's following Moore's law and we're growing the number of transistors in this very large way, we're still not able to run algorithms that are able to basically tackle these exponentially large spaces. And so this is one of the major challenges with digital computation, and this is extremely common. And so I think when you hop into computer programming and you take an intro to computer programming class, you have this idea that, I'm just going to write some algorithms and I'm going to say, I'm looking for a plane flight between this location and that location. I want it to be the cheapest plane flight possible. And so I take all possible cities that I could fly to, and then all possible cities from that location I could fly to, and then all possible cities from that location. And let's say you want to map a route around the planet where you visit, the 50 major cities on the planet, and you want to do it in a cost-effective manner. Well, this is actually an exponentially large problem. And it doesn't even seem that wild or that uncommon, right? If you want to go visit 50 places and do it cost effective, this seems like a realistic problem that someone would want to go tackle. However, the number of possible combinations is equally as hard as this deck of cards, right? There's 50 different locations times 49 other locations. So you could go to any of those 50 first, then any of the remaining 49, then any of the remaining 48. And so even with visiting 50 locations, the number of possible paths you could take to visit all of those is exponentially large. It's mind-numbingly huge, and we are terrible at even comprehending and thinking about just how big this space is. And so what's really fascinating here is, you go into this intro to computer programming class and you just think, I'll just code up this program that searches all possible paths, and you hit play, and then you're sitting there for 20 minutes and you go, wait, why hasn't my algorithm spit out the correct answer yet? And then you realize, it would actually take 2 trillion years to come up with this answer, let alone me sitting here for 20 minutes, right? And so most computer programming classes are figuring out little shortcuts, little hacks. How do we reduce the space? How do we come up with basically a hack to figure it out in a quicker manner that we don't have to search all possible paths, right? And so quantum mechanics offers novel solutions to various types of problems. And in a future video, I'll cover some of these algorithms which have this exponential speed up, because those algorithms are the ones that probably have the greatest potential to be applied in a really meaningful, sort of revolutionary way. Okay, so why am I talking about this exponentially large space that quantum computers are potentially processing and integrating information across? Well, the reason is twofold. One reason is just to really emphasize the importance of this technology and why it's going to be so groundbreaking when it hits. We're talking about a level of computational power that really numbs the mind, and our modern digital computers will pale in comparison. And this is going to be a revolution on the order of magnitude of inventing digital computers in the first place. Another reason is it's really important for our conception of self, because, we think about our brain as a digital computer. Very common for people to talk about artificial intelligence in this digital computer way and talk about the brain as the digital computer. And that's non-controversial and very commonplace. However, imagine we were able to have quantum computation in our brains. The level of inaccuracy of our current models about the brain are staggering. It's staggering just how greatly incorrect we are potentially about understanding our own brain. 200 billion neurons and all these trillions of synaptic connections, but those are all digital in modern framings to many degrees. If there was the capacity to have 1,000 quantum bits, that is so exponentially, wildly, astronomically more powerful than 100 billion digital neurons. Right? The scale up is absurd. So even having low qubit counts relative, is amazing. And then imagine there was anything in the brain that was on the order of 100,000 qubits, right? We're talking so many zeros following, your number, that the space of what is being processed is so immense that it truly just breaks the mind to even comprehend what's going on. And if our minds are tapping into any computational power on that order of magnitude, it's mind-numbingly different from modern conceptions of digital computers and could totally revolutionize how we think about ourselves. All right, so we have quantum computers. And current quantum computers are anywhere on the order of 50 qubits to some groups claiming to be having 100 or 120 qubits. And I had the privilege a month ago to chat with Hartmut Nevin, who's the head of the quantum AI group at Google at a consciousness conference. And I basically asked him, what is the state of quantum computers? What's holding this up? Why don't we have quantum computers in front of us? And his answer was essentially that quantum error correction is the next frontier, and we don't have that figured out just yet. And so while the quantum computers are growing in size with time on an exponential scale, and now we have 50 and 100 qubit quantum computers, the enormity of the space that they're searching is non-trivial. And so let's simulate in your mind that we've run some quantum computation and we have the correct answer. So the quantum computation's being run. There's this wave function of different probabilities of choosing this option, choosing that option. And we've created this constructive interference so that the correct answer is amplified in its magnitude of probability of being selected, and all the incorrect answers are dampened, right? This is typically how a quantum computer runs. You amplify the optimal solution, and then you destructively sort of wipe out, deconstruct the incorrect answers. Then you go to measure the superposition for your quantum computer, and you get a probabilistic output. So it means that for each possible output, there's a certain probability given by this wave function. And when you measure it, you probabilistically get an output out of this quantum computer. And so the problem that they're running into currently is that because the space is so giant, even if you amplify the correct answer to a very high degree, in practice, there's a lot of error introduced in the imperfection of our human instruments, right? So we're creating these quantum computers and they have imperfections. And so those slight imperfections make it so that once you hit these exponentially large spaces, there are so many wrong answers and only one correct answer, right? Even if the correct answer is trillions of times more likely than the incorrect answer, or than all the incorrect, any given incorrect answer, there's so many incorrect answers, trillions to the trillions to the trillions of incorrect answers, that is still going to happen. And so when you measure your quantum computer, you get a bunch of garbage outputs. So this is a huge problem. So what needs to be introduced? So what is currently being worked on now is quantum error correction. And long story short, and I'm not going to go into all of the details because it is quite complex, and I have, some understanding of this, but definitely am not an expert. Quantum error correction is being developed and will be able to overcome the level of error that's being generated from the environment. And so, have hope, it will happen. There's now a lot of work going into quantum error correction, and there's an exponential growth, an equivalent Moore's law applicable to quantum error correction, where we're able to reduce the error more and more with our growing technologies. And so we will be able to make feasible quantum computers in the very near future. All right, so real briefly, what is error correction? So I'll give you the digital example, and I referenced this a bit earlier. You have a 1, it needs to stay a 1. You have a 0, it needs to stay a 0. In digital computers, a very simple error correcting code would be, let's take, every time we have a 1, let's have 5 1s. And every time we have a 0, let's have 5 zeros. And then we wait an amount of time. And basically a cosmic ray, some sort of interference from the environment can come in and flip one of these bits. And so your 1s become a 0. So what you can do is you can check, I'm supposed to have 5 1s, but guess what? One of them got flipped. Now I only have 4 1s. Now I recognize, okay, one of them is off, the other 4 say it's a 1, so I can just flip that 0 back into a 1, right? And this is no joke. This is actually how digital computers work. Your computer is trying to sustain 0s and 1s into the future, but there is a random chance that microwave radiation, cosmic rays come in from space, hit your computer and flip your 0s and your 1s. And basically there's just a level of chaos in our reality that we need to correct for. And so your computer is systematically scanning through your hard drive, scanning through your memory, and your CPU, as it's processing information, is constantly, checking the binary, checking the 0s and 1s that they are what they say they are. And so the challenge is that in quantum computers, we're dealing with quantum decoherence. We're dealing with environmental decoherence, which is so much more powerful and so much more of a struggle than with digital computers. So digital computers, you got cosmic rays. In quantum mechanics, we need to sustain these really subtle quantum properties, and they're constantly being interrupted by the environment. And so quantum error correction is essentially a very important advent that needs to be used in order to make quantum computers practically feasible. And it is very much akin to digital computers, where essentially you have some sort of quantum bit that's your primary input, and you essentially create an encoded quantum bit where you essentially entangle your quantum bit with 2 other quantum bits, and you create a register of 3 quantum bits, which is sort of the encoded version of that one input quantum bit. And then you can essentially run a way of doing a checks and balances where you can then restore the original quantum bit back to its input state. And so in quantum mechanics, it's a little bit different than digital. So in digital computers, you have zeros and ones. In quantum mechanics, you can have a greater variety of things that can happen. So you could have a bit flip between 0 and 1, but you can also have a phase flip. And so qubits have a additional phase dimension. You can imagine there's a 0 and a 1 and a plus and a minus. And this is more of an accurate representation of a quantum bit. And so you can have a flip in the phase dimension, and you could have both of these occurring. So you could have a bit flip and a phase flip. And so in a quantum bit, in a quantum computer, the simple solution to error correction is actually that you have 1 qubit and 1 target qubit and 8 error correcting ancillary qubits, right? And so in this setup of 9 quantum bits, you're able to figure out if there is a chaotic environmental bit flip or phase flip, or a bit flip and a phase flip. And so there's essentially 3 different types of problems that could occur, and you're able to detect which, if any, of these 3 problems occurred, and then apply the solution to that original system and sort of flip it back to what it should be. Now, there's a bunch of details around, the practical aspects of a quantum computer, which I'm not going to go into. But essentially, there is a way where you could have your quantum bit entangled to these control bits. You can measure the control bits, figure out what gate needs to be applied to your target bit, apply that gate if needed to your target quantum bit, and then continue carrying on with your quantum algorithm, right? And since the sort of original inception of this 9 qubit solution for every single quantum bit, there is now sort of a more cleverly implemented 5 quantum bit solution where every single qubit now has 5 qubits, which represent that single qubit. And so there's a way of sort of sustaining these subtle quantum information processes and actively applying error correction to maintain the quantum information of your target system. And so this is what's called fault-tolerant quantum computation. And so there's a way that people are now working on where you design quantum gates where the sort of algorithm that you're running is taking these sort of encoded multi-qubit registers that represent just a single quantum bit, and then running a gate on these encoded registers, and then applying error correction very frequently onto the system, and then sort of like measuring, classically inputting the correction operation that you need to apply, and then carrying on the algorithm. And so there's a lot of infrastructure that's being built right now to make this feasible, to build fault-tolerant quantum computation. And what's really important to keep in mind here is that this is only a polynomial or like a linear increase in hardware in order to create these fault-tolerant quantum computation. So let's say you have a quantum computer that is able to sustain 100 qubits. Now, every 5 of them is actually just going to be one usable computational target quantum bit, and all the other ones are redundant and used for error correction. So what this means is that your 100 qubit quantum computer is actually just a 20 qubit quantum computer. And so I think this is really important for us to keep in mind when we hear about in popular science about various quantum computers that are on the market. a lot of these quantum computers do not have error correction and are not properly controlled, so they sort of lose their feasibility as they grow in scale. And then even if they do have error correcting code, you essentially need to divide the number of quantum bits that are advertised by 5 or even maybe by 9. And so, 100 quantum bit systems might only be 20 quantum bit systems. And while those are still giving us a, massive improvement above some digital computers, they are not at this like massively exponential size that we need to have this sort of paradigm shift in technology. So keep that in mind. But even with that, if we're able to make 1,000 qubit system divided by 5, we still have a 200 qubit system, and then we're able to run algorithms that are potentially processing these exponentially large spaces and giving us this massive computational speed up. So despite error correction, we are still going to have this exponential explosion in quantum computer technology. But I think a lot of our estimates of when this is going to happen need to be sort of calibrated within this error correcting framework. So keep that in mind as you go out and read about modern systems. All right, next up, I'm going to talk about what this means for biology. And I think this is really a fun new way of solving some age-old quantum consciousness problems. So the classic thing you hear is, well, haven't you heard that biology is warm, wet, and noisy, and so there's no way that your quantum computer could ever be sustained in a biological system. And so there's various attempts to address this sort of limitation, and essentially no one is arguing that quantum computation just shows up for free in nature, but that through billions of years of evolution, biology has been orchestrating ways of sustaining these very subtle quantum properties because they provide a computational speed up. It's not just for fun, it's because biology is optimizing problems. It's coming up with computational solutions to very hard problems, and quantum computers provide a computational speed up, and so it's advantageous for biology to build quantum computers or biologically plausible quantum computers. And so previous episodes I've discussed how having these decoherence protected spaces is really important, right? So you want to fight off environmental decoherence. The chaos from the environment needs to be kept at bay while these subtle quantum properties are allowed to sustain. This is the same problem that quantum computers are facing right now. And so the question is, how is biology doing this? And granted, there is no clear answer at this exact moment, but here is a novel theory for you. So in a previous episode, I pitched that the Stewart-Hameroff-Roger Penrose model of quantum computation in biology, which is looking at microtubules. Microtubules have this bizarre property of being a single protein repeated in these helical shapes. And so one idea is that there's these topological quantum bits where delocalized channels of electrons are essentially sustained in these spiral-like patterns throughout the microtubule. And then the sort of electric flow properties within these tubulin proteins, within these channels of delocalized electron clouds, those serve as your basic quantum bits. But here's the question, right? If environmental decoherence is so strong, are we going to have usable quantum computation? So one idea would be that these microtubules, and I haven't seen this proposed elsewhere, so this is sort of my own novel proposal here, that these different topological qubits could be these redundant registers, right? You're not just having every topological sequence as an independent quantum bit, but entire microtubule topologies of neighboring spirals within the topology these are serving as a highly entangled register where a single quantum bit is encoded into a more distributed system, and this creates a little bit of fault tolerance. And so what if we were to conceptualize each of these microtubules as sort of a fault tolerant quantum register, and then neighboring microtubules are doing the same thing? They're another quantum bit running parallel. And then there's these microtubule associated proteins, these sort of channels that link up various neighboring microtubule systems. And so this would be sort of when you want to entangle these different quantum registers. So each microtubule is a quantum register, and then the logic gates are sort of implemented via these connecting proteins between the microtubules, you know. So somewhat speculative, but this would provide some sort of fault tolerance, and it would create a little bit of a solution for how biology is able to sustain quantum computation, right? Not only is it creating protected spaces, but it's trying to produce fault-tolerant, redundant systems for the sake of error correction. And so here is yet another iteration upon this. And once again, I don't know what would actually be doing this in biology, but we will be developing quantum computers and are developing quantum computers in the lab, which will measure a fraction of your quantum bits and then apply a gate operation onto the remaining quantum bits within the system. And so what this is doing is it's estimating environmental decoherence processes and then creating sort of the inverse corrective measure that is then applied onto the quantum system. So imagine, and there's a little bit of research out there on this, that if you are able to estimate the environment and then apply error corrective operations upon the system, you're actually able to actively counteract decoherent processes. And so potentially, not only is biology maybe finding a way to sustain quantum coherence via protection from the environment, but it's actively estimating the decoherent forces in the environment and then creating, in a way, sort of like noise canceling operations that then are able to even sustain quantum coherence in a more active way. Using the Penrose-Hameroff model, because what other models are there out there for quantum computers in biology? If there are some, we could, speculate on what these mechanisms might look like for those systems. But you have a microtubule system. There's environmental decoherence being applied onto it. And then imagine there's some sort of protein system that is measuring part of the overall registry, getting the output of that measurement, and then that protein is then coming around and then applying some sort of gate onto the remaining quantum system in order to cancel out the estimated environmental destructive force, right? So you're essentially siphoning off the error from your system and then applying a corrective gate onto the system, not measuring the system. That corrective gate operator applied to the system is then able to sustain the quantum coherence even further. And so here's sort of the big whammy from this, wild error correction theory. The idea would be that, is consciousness able to emerge within the presence of quantum error correction? The theory being that the advent of quantum error correction in biology is the creation of human consciousness, fundamentally. By being able to quantum error correct, quantum computations become useful all of a sudden. Now that there's useful quantum computations, you're able to sustain a conscious entity into the future. You have that unity of self through time that is suddenly apparent and suddenly emergent from this error correction. And so could we maybe one day find some sort of error correction procedure in biology, and then that procedure is now functionally equivalent to the emergence of human consciousness in early biology? And this probably would occur at some sort of single cellular level, I would speculate. But this would be what sets apart raw proto-conscious quantum computational forces that are not being error corrected and are sort of not practical to some degree. Or you have error correction and then consciousness now emerges, right? So this is sort of an alternative to the Penrose model, where Penrose suggests that the ability to have objective reduction is the emergence of human consciousness, or consciousness at a fundamental level, and then human consciousness is like an extension or an expansion of that basic process. Potentially error correction is an alternative theory for how consciousness suddenly comes onto the scene of these primordial quantum computers in early biology. So that's a fun theory. I haven't seen that anywhere else. I kind of came up with it in developing this episode, so let me know what you think out there. The alternative is that there is no error correction in the human being, and the nature of our mind is brute force quantum computation. Maybe human inventions of quantum computers will have this fancy form of error correction, and that error correction that we're inventing is some sort of like novel advent only in the technological sphere. And human consciousness and consciousness in biology is characterized by generate these massive entangled quantum computational forces, and they're searching, 2 to the 100,000th power computational spaces, maybe within a single cell. And then that single cell is hitting 2 to the 100,000th power, and then the information that's being processed is being funneled into just a few different behavioral activities. And so through that funneling of this massive computational power with zero error correction, you accept the decoherence forces from the environment. All that matters is generating a massive macro quantum computation. You accept the decoherence, and then the organic, mushy human nature to the quantum computation is just all of that raw error of chaos from the environment. And then when the wave function collapses, when a decision is made, it has so much raw computational force behind it that somewhat overcomes, the funneling of that overcomes the destructive decoherent forces from nature. So, open-ended question. I don't know what the answer is. What do you think out there? Is consciousness enabled through quantum error correction, or is consciousness occurring because of the raw computational power that's possible in quantum computational systems? More on this to come, and I'll talk to you again real soon.